Okay, and you can talk to Irina through this.
Okay, and this is a talk by Irina about static analysis for transitioning to CHERI. And let's start.
Hi, my name is Irina Dudina, and today I'm going to talk about static analysis for transitioning to CHERI C++. So let's talk about CHERI first. CHERI stands for Capability Hardware Enhanced RISC Instructions. It extends conventional hardware architectures with architectural capabilities. It enables fine-grained spatial and temporal memory safety and scalable software compartmentalisation. It reuses conventional software stacks based on virtual memory and C++ and supports smooth incremental software transition within existing ecosystems. It provides extensions to MIPS, RISC-V, and ARM. And ARM have developed a processor prototype and evaluation board called Morello. So let's look at CHERI protection. Let's say we have a simple C program. Here in function main, we have a local array of 3 elements, an additional local variable secret, and we pass an address of this array and its size to a function foo that is supposed to print all the elements of this array. However, there is a bug in the implementation of function foo. We should be having strict comparison here instead. So we'll be having an off-by-1 error in function foo and printing 1 extra element. So if we look at the memory layout of the sec frame of function main, we'll see 8-byte pointer, then 3 integers of an array, and then 1 extra integer secret. And if we print 4 elements starting from the first element of the array, we will have our secret leaked. Now let's take the same C program without any modifications and just recompile it to CHERI and run on CHERI architecture. So first thing we'll notice is that our pointer now is 16 bytes long and is implemented as a capability. It means that in addition to an address value that points to the start of the array, we also have bounds, so a range of memory addresses of the object that this capability points to, and permissions for the memory access. So now every time when we are using this capability to access memory, hardware will check whether this memory access complies with bounds and permissions of this capability. This is true for the first 3 iterations, but on the last iteration of the array, we will have an out-of-bounds access. So this will result in hardware trap. Therefore, CHERI will protect this vulnerability in function foo from being exploited. Now let's take a closer look at CHERI capability. Here we have a typical 128-bit representation. It contains 64-bit address, bounds in a compressed form, permissions, and other metadata. Also, every capability on register or in memory is supplied with out-of-band software inaccessible validity tag. So any attempt to tamper with the representation of this capability, for example, manually changing bytes that represent permissions, will result in clearing this validity tag and this capability becoming unusable. As we've seen in our example, all dereferenceable pointers and implied virtual addresses like return address or PLT entry are implemented as capabilities in CHERI. And this is seamlessly supported by compiler, language runtime, and operation system. So one of the key benefits of CHERI is that you can take C++ source code and with minimal modifications, recompile it to CHERI and immediately benefit from the memory safety that CHERI offers. So the amount of changes that you need to make in terms of lines of code is reported to be very small. It varies from 1 or few % for low-level system pointer-heavy code, and it's a few orders of magnitude less from it for a general purpose code. Additionally, many compatibility issues are detected and well explained by the compiler during compilation. However, there are certain issues that are not detected by the compiler and only uncovered during runtime. So it would be really nice to have a static analysis tool that can uncover more compatibility issues statically. So although our whole CHERI project is about memory safety, I just want to emphasize that in our static analysis tool, we will not be looking for out-of-bounds memory access or another vulnerability. We will be looking at portability issues, so patterns of code that work fine on the architectures it was originally written for, but will not work on CHERI. One landmark example of such transition from one architecture to another would be a transition from 32-bit architectures to 64 bits. So we more or less know what kind of problems arise during that kind of transition. And impact of CHERI on C++ programming model is well studied and discussed in these papers. So main things are increased pointer size and alignment, which often breaks legacy code assumptions. Pointer provenance means that we cannot modify parts of a capability or copy a capability not as a whole, because that will lose the tag. Also, CHERI affects pointer representation, which has an impact of the semantics of the pointer equality, and affects certain programming patterns, like using bitwise arithmetic to align pointers, for example, or storing metadata in the unused bits in pointer representation. So we developed our static analysis tool in the Clang static analyzer framework, which is part of Clang compiler, and we used a downstream version of Clang that has CHERI support. Clang static analyzer is extensible with custom checkers, and it provides two levels of analysis: path-sensitive interprocedural checks via symbolic execution, and simple syntax-level checks via AST matches. So let's talk about just a few checkers that we have implemented. The first one is about pointer alignment. So any unaligned memory accesses in C is a UB on any architecture. An unaligned access can result in a fault, affect atomicity or performance. However, these alignment issues may not manifest in real world due to certain several reasons, like ABI guarantees or fragile properties of a current data layout, or just choices made by a compiler. But when moving to another architectures, all these properties may break, and the code will become not portable. Even if the pointer access is really unaligned in runtime, the ill effects on certain platforms like x86, for example, can be so subtle that no one will notice or no one will care about these issues. However, on CHERI, these issues, alignment issues, become more pronounced. First of all, because the alignment of capabilities are so big that it easily breaks legacy code assumptions. Also, unaligned loads or stores of capabilities always generate a runtime hardware exception. That's because these validity tags are only exist for capability aligned 16-byte aligned memory locations. Additionally, if you're trying to memcopy a capability through an unaligned memory, for example, temporarily memcopy to unaligned address and then copy it back to the aligned address, this will result in memcopy function splitting the capability in two parts when copying it, and therefore that will clear the tag in the copy. And even if you then copy the capability back to the properly aligned address, you will not have the tag back. So your capability will be invalid, and you will only notice it when you will try to reference it. So this issue will be hard to investigate. So in order to detect this, we created a symbolic execution checker that reports casting of underlined pointer values to capability aligned pointer types. Also, it reports storing not properly aligned pointers to capability pointers, and an attempt to copy a capability through an underlined memory. In order to report this, we track pointer and integer alignment, relying on type restriction, pointer and integer arithmetic, and aligning attributes. And we also track memory regions that may contain capabilities. So let's take a look at the example of one of the warnings. So here we have a pointer to the structure that contains capabilities. Therefore, this pointer must be, the value of this pointer must always be capability aligned. And this is passed for an initialization to this function. And this function assigns an address of a flexible array field to this pointer. And this flexible array field is not properly aligned. So this allocated memory will be unaligned, and the structure stored there will have unaligned capabilities. So these capabilities will not be valid or will lead to hardware traps. So in this case, we are kind of lucky that we actually have the call to the function that asks to allocate memory for capability aligned object. But this kind of functions are often implemented in the library, and also due to the limitation of an procedural analysis, we may not have this call reachable. So we want to still be able to detect this kind of unaligned memory allocation. So in this case, we can argue that this pointer to void, we don't know the type of values that are supposed to be stored there. So we can argue that this might be designed to store capabilities there. So this memory should be capability aligned. This is the heuristic we use. Any external pointer to void, external means global variable, structure field, or function parameter of top-level function in the analyze call stack. So any pointer to void can potentially be a pointer to capability, and all allocated or assigned memory should be capability aligned. So we'll discuss the implication of this heuristics later. So another checker is capability copy checker. It detects custom implementation of copy routines that perform a piecemeal copy that will, during copying, break capabilities in several chunks, like in chunks of this size of long, like in this example. So the problem is that the resulting capability, if we were copying capabilities here, the resulting capabilities will not have the validity tag set because we didn't copy it as a whole. So this is implemented as another symbolic execution checker. And again, we are using this heuristic about void star assumption because this is a library function. We may never see an actual call of memcopy with an attempt to copy capabilities with it. So we have two more checkers. One is working with capabilities to integer conversion. So here we have This is also a symbolic execution checker. Here we have conversion from pointer to not capability type. Pointer diff-t is just an integer type in CHERI. Therefore, we will lose provenance here, and resulting aligned capability, aligned value will not be a valid capability. So another example is CHERI incompatible pointer arithmetic. For example, here we're trying to perform a branchless select on pointer values. So we're XORing two pointer values, but on CHERI, capability can only be derived from a single other capability. So we cannot choose here which side to derive a capability from. Either would be wrong. So this code will need to be rewritten, and this checker detects such cases. And the last checker just detects conditionals where we check pointer sizes and fail to consider 128-bit pointer sizes. This is a very simple ISD checker. So we evaluated our static analysis on the selection of a CheriBSD ports. So CheriBSD is a FreeBSD with CHERI support, and it has its own ports tree. So the total amount of analyzed code was 2.5 million. We found that the most useful warning is useful checker is the one that provides alignment warnings. So we could see that warnings that rely on this void star assumption have significantly lower true positive rate, but we do not want to abandon this assumption because therefore we will lose some very good true positives that are hard to detect and investigate otherwise. So same applies to the second checker, text stripping copy of a capability. Again, such low true positive rate is explained by this assumption, but we actually detected a custom implementation of memcopy and qsort and other tag stripping functions. So the pointer to integer checker has higher true positive rate here, but these warnings are mostly intentional code, so this won't be fixed. So we don't find this checker very useful for this particular selection of packages, but we've seen other good examples of warnings for this checker in other projects. And the last checker has only one warning, and that was true positive. So as a result, we added CHERI support to Clang static analyzer, implemented 4 CHERI-specific checkers. We had to adapt build interception tool scanbuild to CheriBSD to be able to perform analysis on Umbrella. We evaluated our static analysis on a subset of CheriBSD ports and reported a few fixes, some of them already accepted. And there's more to be done in this direction. We could use static analysis to provide suggestion for the code patterns that could be slightly changed to benefit even more from CHERI protection. So this is marked as future work here, but this is actually has been already done after we submitted our paper. So this is it from me today. This talk was delivered to you from CheriBSD running on an ARM CHERI platform. Thank you for your time.
So thank you, Irina, for the talk.